This meeting is being recorded.
In this next video, we're going to look at how we can balance these redox equations that we're going to utilize in these electrochemical reactions. So in the past, you've balanced reactions to the point where you had the same number of atoms on each side, but you may not have had to balance the charge on each side. So that's going to be the main difference with balancing these redox reactions. We also have to balance a charge by adding electrons. So we're going to look at what is generally considered the easiest method, this half reaction method, where we can consider oxidation reduction reactions separately. So we can take our overall equation and break it into two halves. So we're going to utilize this half reaction method with an example given below here. So we have the steps listed here, 1 through 7, the main steps. In step 3 here, we're going to break down this balancing of each half reaction separately. Then we'll combine our two equations, and we'll make sure that everything, including mass and charge, are balanced at the end. So we have this scenario here that we have this titration reaction that's happening between our permanganate ion over here and then this oxalate ion here. So we have what's given below, the reactants and the products that we need to consider to start this half reaction balancing method. So first step is we're told to assign oxidation numbers to determine what's oxidized and what's reduced. So you can do this before you get started. It is not absolutely necessary to start the process, but I'll give you the oxidation numbers just so we know ahead of time. So I've solved for manganese here by setting this permanganate ion equal to -1, and then we have -2 for each oxygen times 4, so that's -8. Plus manganese. So if you rearrange this, we would end up solving that manganese on the reactant side is +7. Over here, we know it's +2. So that's really all we have to do to know that we go from +7 to +2. So therefore, our manganese half reaction must be the reduction reaction. And then our carbon here must be oxidized. That's the half reaction. And I know that because I know that oxidation and reduction always occur together. The oxidation number for my oxygen does not change in either species here. So I know that it must be the carbon, and just for the sake of knowing for sure, I'll give you those oxidation numbers. You can solve for those either from the neutral compound CO2, you get +4, and then the oxalate ion, set that equal to -2, you get +3 for your carbon. So you can see that that definitely increased. So carbon was our oxidized species. All right, so let's, we'll break these reactions in half, and then we'll go back up and follow the next steps. So I have MnO4, and that will give me manganese 2+. I know which reaction, which product to pair with which reactant because it has manganese with it. I have C2O4, 2 negative, and that will give me CO2 in this half reaction. All right, so again, this is going to be my reduction, just to keep us acclimated as to what side of the equation we might want to add electrons to. All right, now that we have broken the oxidation and reduction reactions into two parts here. Now let's balance each half reaction. So we want to balance everything other than hydrogen and oxygen first, because we can fix those later. So manganese, I see I have 1 of each in my reduction half equation, so I can move on to my oxidation half equation. I see that I have 2 carbons, and I only have 1 on the CO2 side, so I have to add a coefficient there. All right, so that's the only thing that I've done so far. Now my carbons are balanced, my manganese was already balanced. Now I'm going to move to step 3, part 2 here. I'm going to balance the oxygen in both half equations by adding water. So each water molecule will add one oxygen atom. So I see with my reduction, I have 4 on this side, I have 0 on this side. So now I'm going to add 4 H2O over here. So that adds 4 water molecules, but my oxygens are now balanced. On the other oxidation half of the reaction, I have 4 oxygens on this side, on the oxalate ion, but I have 4 when you multiply this by the coefficient of 2, so I don't have to add any water to that half reaction. All right, now we want to go back and balance the hydrogen next, and we're going to do that. We're going to balance this in acidic conditions. So we are going to add H plus hydrogen ions to balance our hydrogen atoms. So we see with our reduction equation, the side with manganese has 0, or I'm sorry, the side with the permanganate has 0, the side with the manganese ion has 8. So I'm going to add 8 H plus to the side, and now I'm balanced as far as my hydrogens go. There's no hydrogen in the second, the oxidizing half reaction, so we can just skip ahead to the next part. Last but not least, we're going to balance the charge by adding electrons. So what do I mean by that? How do we know what the charge is? Each of these species, we could write a charge above. So this would be, or below here, we'll write +8 for 8 hydrogen ions. So we know that 8 times +1 gives us +8. We have 1 permanganate, so we're going to add -1 here. Then I see I have +2 for my manganese, and then I have a neutral compound as water over here for my other product. So I'm going to write that as 0 for my oxidation number. So I see that I'm going from the sum over here of +7 to +2. So there's a difference of 5 electrons between that, right? A difference of the number 5. So the only way that I can correct this is by adding a negative. So I'm going to reduce over here by adding 5 electrons. So now my half reaction is going to be 5 electrons plus 8 H plus manganese or permanganate MnO4 negative gives me my Mn2 plus 4 H2O. All right, so that's my whole half reaction there. Next I have, do I have to balance the charge here? Yeah, so I have -2 on this side. I have 0 over here, so I have to add 2 electrons. So this half reaction is going to be C2O4 2 negative, gives me 2 CO2 plus 2 electrons. Now, notice that we have a different amount of electrons going in as out. So we're adding 5 electrons. So I'm going to multiply this by 2 because I need to have the same amount going in as out. And then over here, since 2 are coming out, I'm going to multiply this by 5. So now I'm going to combine, after I distribute that 2 and that 5, I'm going to combine all of my reactants and products here. So on this side, I get 10 electrons plus 16 H plus 2 MnO4 negative. From this equation over here, I'm going to get 5 C2O4 2 negative. And that's it. And then I have my products. So don't forget the 2 over here for the manganese. So 2 Mn2 plus. Plus now I'm going to have, oh, this should have been 4 H2O. So now I'm going to have plus 8 H2O. And then my other products will be 5 times 2 or 10 CO2 and 10 electrons. Now you might notice that the electrons are kind of like a spectator ion. We have 10 in, 10 out. We can cancel those out in our overall equation, and our final overall reaction when we're balanced in acidic conditions here will look like this. So we're going to have just carry everything down. 16H plus 2 MnO4 negative plus 5 C2O4 2 negative will yield 2 Mn2 plus 8 H2O plus 10CO2. If you happen to end up, in this case we don't, but if you did happen to end up with H plus on both sides or water on both sides, you could cancel that out and simplify even more. So some future examples will look at that. And this is balanced in acidic conditions. We will also take a look at balancing in basic